Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. Today we're going to look at the formula, the general formula and then more specific formulas for pyramids and cones, whereas in our last lesson we did prisms and cylinders. So before we get going, let's see if we can apply the same formula we did for prisms and cylinders to pyramids and cones. So let's think about that right here. Pause the video. And I guess I already say we won't be able to apply that formula, but think about why not. And again, this is the formula you want to think about. V is equal to the area of the base times the height. Why will that formula not work for pyramids? Okay, so hopefully we see that, well, for pyramids, these cross-sectional slices get smaller and smaller and smaller as we approach that point at the top. So if we just take the area of the base times the height, that's assuming that the cross-sectional areas are congruent to one another as you move up towards that point. Right? If I have we'll just do a triangular prism. Right, as I take the cross-sectional areas, they're all congruent, right, as I move up the prism. So it makes sense to do the area of the base times the height because you're just stacking congruent figures on top of one another. For pyramids, you're not, right? You're not stacking congruent pieces. You're actually stacking similar pieces, but they do get smaller as you approach that point. So we won't be able to use the prism and cylinder formula, but we'll see if there's a variation of it that we can use. And to try to figure out what this formula should be, we are going to do a little water demo. Let's go down here. Now, originally I planned on doing this water demo myself and you'd be able to watch me do it over video, and then I realized, well, I only record my screen. I'm not recording myself when I'm talking, so that's not going to work. So you guys are going to click on that YouTube link. It'll take you to another video, and it'll kind of go through this experiment that we would have done in class or that you would have seen me do. One thing to take note of, and let me just kind of explain the experiment because they don't do it on video. It's just a silent video. They're going to fill a cone with water, and they're going to pour that cone into the cylinder. And they're going to see how many cones does it take to fill up the cylinder. Now there's some things we need to know before we start watching. The cone and the cylinder have the same diameter, or they have the same radius. They also have the same height. So that's important. They have the same exact dimensions, except one's a cone, one's a cylinder. So that's going to be important when we think about how to figure out the volume of the cone based on the cylinder. So before you even watch the video, take a guess. How many cones do you think it will take to fill up that cylinder? So we're going to keep filling cones until that cylinder is completely full. Okay, go watch the video and then come back and we'll kind of discuss how we can derive this volume equation. All right, so after watching the video, we saw that it was 3 cones to fill the cylinder. And that was exact, right? 3 perfectly full cones filled the cylinder perfectly full. Well, let's start to answer these questions. The volume equation of a cylinder. Well, we know what that is, right? That's volume equals area of the base times the height. More specifically, volume equals pi r squared times the height. And if it took 3 cones to fill the cylinder, and they have the same radius and the same height, how could we change the volume formula for a cylinder to make it the volume formula for a cone? Pause the video, see if you can figure it out. Well, there's 2 ways we could write it. If we want to use the most specific formula, and that's what we'll use for now, we could do 1/3 pi r squared times h, or you may see it written as pi r squared times h over 3. Both of these will give you the volume of a cone. Now, what's nice is that we can actually generalize this to all general cones, right, which include the pyramids as well. So, volume of a pyramid and this is regardless of what the base is. Volume of a pyramid is also going to be 1/3 area of the base times the height. So regardless of whether it's a pyramid, whether it's a cone, it's going to be 1/3 of what that prism would be if it had that base, right? Or what that cylinder would be if it had that base. Okay, now that we have our formula handy, let's go up and apply it to certain problems. And that's obviously what would go down here. We just put it there. Let's jump all the way up here. Let's actually do number 3. Number 3 is a bit of a tough one because you have to do some work to find some of the dimensions you need. So pause the video, see if you can find the volume of this cone right here. If you can do this one, you probably can certainly do 1 and 2. All right, so we know that our general equation is volume is equal to 1/3 area of the base times the height for this cone. I hope I'd said cone before. Now I'm thinking I may have said cylinder, but we know it's a cone. Specific formula, 1/3 pi r squared times h. Now we know the radius, right? We know that's 30 millimeters, but we don't know the height, right? We know the slant height, 54, but we don't know the perpendicular height of this cone. So we got to find that. If we are assuming this cone is right, which we can, we're not going to assume that we're trying to get or that they're trying to trick us or anything. So we'll use the Pythagorean theorem. So I get 30 squared plus h squared is equal to 54 squared. I did this whole video once before and had to restart it because I did 45. I just read it backwards. Didn't realize it until the very end. So here we get 900 plus h squared. I have to break out the calculator for 54 squared. That gives us 2,916. Subtract 900 from both sides. I get h is equal to 2,016. And the square root of 2,016 is approximately 44.900. Again, I'm just rounding to 3 decimal places in the middle of the problem. I do believe it says to round to the nearest unit for our final answer. So I just come over here and I substitute in my dimensions. 1/3 pi times the radius squared, so 30 squared, times our height, 44.900, and that gives us a volume of, again, bring out that calculator, approximately 42,317 cubic millimeters. It's a lot of cubic millimeters. All right, let's go ahead and look at a composite solid. We're going to do number 5. This one's maybe a little hard to understand what they're asking us for. This is a prism with a with a square pyramid being taken out of the top. So the area that we're looking for is this area around that triangle. Sorry, not the triangle. The square pyramid. And I should not say square pyramid because it is a rectangular pyramid. Rectangular pyramid that's been removed. So again, pause the video, see if you can find that red volume, and join us back for a discussion. All right, first thing I'm going to do is find the volume of the entire prism. So without this, I keep saying square, it's not. Rectangular pyramid being taken out. So volume of the prism, that's equal to big B times h. And here we just have length times width for big B times h. So we get 25 times 12 times 15. 25 times 12 is 300. 300 times 15 should be 4,500 cubic feet. Now we need to figure out the area, or sorry, not the area, the volume of this rectangular pyramid. So I'm subtracting the pink area. That will give us the red area. And maybe since I drew that in red, right, the red is the entire thing. I need to remove the pink from the red. So if I'm looking at that rectangular pyramid, volume is equal to 1/3 big B times h. Volume is equal to 1/3. Area of the rectangular pyramid's base is just going to be length times width. And then, of course, height of the pyramid. So volume is equal to 1/3 times the length. And again, the area of the base of the pyramid is the same as the area of the base of the pyramid. Or, sorry, prism. So times 12 times 25. And, of course, the heights are the same. So times 15. This is going to be equal to 1,500 cubic feet. Again, it's just going to be 1/3 of 4,500. Now, if the whole thing is 4,500, the part that we're removing is 1,500, well, our final answer is going to be 4,500 minus 1,500. That gives us 3,000 cubic feet. That is the, and we'll just shade this in blue, that would be the blue volume. The blue volume. All right, last thing to discuss is some relationships. We'll skip 7. Relationships between similar solids, or just solids that have their dimensions, or one or more dimensions, scaled by a certain factor. We kind of touched on this back in the similarity unit, and as well as in the area unit as well. So let's just look at number 8. If the radius of a cone is doubled, how is the volume affected? Well, if you think about how we figure out the relationship between, or if we look for the factor that the pre-image is scaled by to get the image, we need to do image volume over pre-image volume. Well, we're dealing with a cone, so the volume of a cone is 1/3 pi r squared times h. That just represents our pre-image. Now, if it's doubled, our image is going to be 1/3 pi, and then I have to square 2r. And I got to square both the 2 and the r. So this gives us 1/3 pi times 4r squared times h, all over 1/3 pi r squared times h. Now it's pretty easy to just simplify, and we're left with 4. So if just the radius is doubled, then the new cone will have a volume that's 4 times as great as the original volume. The ratio of the image's volume to the pre-image volume is 4, so we're scaling that volume up by 4. Why don't you guys try, let's see, we're going to do 9 and 10. Both of them are a little different, actually. 9 is pretty similar to what we just did for 8. 10, we're kind of working backwards. It tells us what the what the ratio should be equal to, and then we kind of have to figure out what the effect on the radius is. But let's do 9 first. Pause the video, we'll discuss, then we'll pause the video, do 10, and then discuss as well. Then we'll be done. All right, so for 9, we are dealing with a rectangular prism. It says the length, width, and height of a rectangular prism are tripled. What is the effect on the volume? Well, we're going to look at the volume of the image over the volume of the pre-image. Again, looking for that ratio. Pre-image, the volume of a rectangular prism, length times width times height. For my image, I am scaling all of those up by 3 because we're tripling. So 3L times 3W times 3H. The L's, the W's, the H's simplify, and 3 times 3 times 3, well, that's 27. So if you scale all the dimensions of a rectangular prism up by 3, well, the volume is going to be 27 times as large as the original volume. All right, number 10 says, if the volume of a cylinder is multiplied by 6 and the height stays the same, how is the radius affected? So here, we know that the ratio of the image, and again, pause the video if you haven't attempted this on your own. We know that this ratio is equal to 6. So 6 is going to be equal to the image over the pre-image, but I should come up with some formulas, right? So the pre-image, well, the area of the volume of a cylinder would be pi r squared times h. We know that the height stays the same. So that h can come up here. Pi doesn't change, that's a constant. We're trying to figure out what the new radius will be, though. So I'm actually going to have to do this. These cannot be the same r. So I'm going to have r sub 1 squared and r sub 2 squared. Right? Because we know the radius of the image is going to be different from the radius of the pre-image. So I need to have different r's for those. They're not the same r. Now, let's see what we can do about simplifying this. Well, the h's simplify, the pi's simplify, so we're left with 6 is equal to r sub 2 squared over r sub 1 squared. And my goal, or our goal rather, is to get r sub 2 by itself. We want to see what r sub 2, or the radius of the image, is equal to in terms of the radius of the pre-image. So let's multiply both sides by r sub 1 squared. Don't let the r sub 1s and the r sub 2s confuse you, right? If you want to call one, I don't know, x and one y, that's fine. You just have to realize that they represent the radii of the pre-image and the image. So here we end up getting 6 times r sub 1 squared is equal to r sub 2 squared. Take the square root of both sides to get the r sub 2 by itself. And we get the square root of 6 times r sub 1 is equal to r sub 2. So let's think about what this means. All right, well, it means that the new radius is the square root of 6 times longer than the original radius. So the radius increases by a factor of root 6 from the pre-image to the image if the volume changes by a factor of 6. And that kind of makes sense. If we look up here at number 8, right, when we doubled the radius, the volume increased by a factor of 4, right, which is 2 squared. So, and we're squaring the radius in our volume equation. So if our radius for 10 increases by a factor of root 6, well, root 6 squared gives us 6. Okay, so 2 squared gives us 4, root 6 squared gives us 6. All right, I think that will do it for pyramids and cones. When I see you next time, we will finish our discussion of volume by talking about spheres. And we're actually going to throw in surface area of a sphere as well. Have a good day, and we will see you next time.